They're not actually Hadi. We're just using it to record.
Oh,
Yeah, so I think everyone should be showing up in
and what
person.
happens to the recording?
Yeah, that's a good thought. See, okay, so
First play? No. Can you go back?
oh yeah,
Because I think that's usually how I use it when I
oh sure.
used to teach. So it's used to teach online. So now from here you can go back.
Oh, I see what you mean.
And how do I do this?
I think it is this window here.
Okay. Yeah, and then you can share that window.
Oh, I see.
So if you move, I think the window would stay on.
Yes.
Although this is not showing. Is this both computers are connected?
Just this one is. I just logged into this laptop.
Oh, you're on the Zoom. Okay,
This is what the
I see. I think I was going to say if I can have the other view, just to see what the next slide is going to be.
Oh,
You know what I mean?
the presenter view. Yes.
It's usually easier that way. There's only one screen, right? That's why.
Just one. Yeah.
Ah, because we don't.
We might be able to still do it if you go to slideshow maybe, and then let me see, custom slideshow. I think. It's not it actually. Oh, use presenter view. Yeah, use presenter view is checked.
But it's checked, right?
Yeah.
No, I think the problem is that we are mirroring. We don't have two sides. Can you make it two?
The way it's. Yes, that's right. There is a way to do that. Yep. I'm sorry. There you go.
Okay, now we are two. So now I think if I do this, there we go.
There we go. Okay, let me just. The only thing is, it looks like we just have to share it on Zoom.
Yeah, we do.
I think that would, yep.
So now I'm gonna share this view.
I see. Perfect. Okay.
So what do you see? There you
Okay,
go.
that looks great.
Okay, cool.
Let's make the audio.
Okay, so I think we're good, right?
We are all set. I'll just be in the corner here.
Thank you so much.
No worries.
Thank you so much.
Yeah.
Yeah, that should go into all but for some reason. I will give you.
I think a lot of. We already had to plan out our.
That'll hopefully keep the development.
Great, sounds good. Yeah, I'm excited. 14. Working on September 14. It's a 5 week, yeah. So great.
Hey. How are you? I still don't understand what I'm doing.
Yeah. Yeah.
It's like-
12 and the 19th. Okay, well, I'll keep you updated. Or, well, no, the 19th is at USC, the 12th is at USC, and the 19th is an active 5. Yeah, you have to start. Yeah, is that what you're looking at? That.
Free interns.
Okay.
Great.
Okay. All right.
Not free interns. Free interns.
Yeah. Are you okay?
I'm all set, Joanne. Thanks. Thanks for your help. Yep.
To start, usually 12. 12:10.
Do I have an hour, 40 minutes?
Oh, okay. Well, we should get started.
Oh,
Okay, how are you?
Good. Good seeing you.
Good afternoon and welcome to our first in the IST Research Talk series for spring 2024. I'm Carmen Maitland, Associate Dean for Research at the College of IST, and I'm pleased to introduce to you today Dr. Hadi Hosseini. Dr. Hosseini is an assistant professor in the data science and AI area of IST. He has a PhD in computer science from the University of Waterloo. And prior to IST, he was an assistant professor at RIT in the Department of Computer Science. And he also served as a postdoc at Carnegie Mellon. And today he's going to be talking to us about algorithmic fairness. So take it away, Hadi.
Of course. Thank you so much, Carly, for that nice introduction. And hello, everybody. I hope you're all doing well. This is almost lunchtime, so I'm going to try to keep this talk a little bit light as we go.
Good.
I decided to present like a series of work that I have done in a more high level, rather than diving deep into some of them. But at any point, if you want to ask any question, just stop me and ask. But by the way, I don't know how to get rid of that thing at the top, so I couldn't do it. So hopefully that's not going to impact the talk as much. So I'm going to talk about algorithmic fairness in collective decision making. Okay, so this doesn't work. This works, but this doesn't work. Oh, it works. Oh, it works. Okay. Yes. Okay. So before talking about it, I have to actually tell you what is collective decision. So collective decision making essentially is a way of decision making where a group of intelligent entities come together and they want to make a decision. Right? Now, these entities could be agents, autonomous agents, could be robots, could be firms, could be institutions, could be humans, right? That they have to make a decision on something. And they may have different preferences. I'm going to talk about this in a minute, what I mean. Right? And we see this in all over the place when we're kind of thinking about our everyday life, right? So one of those examples is elections, right? Voting in elections. So a group of people, they have preferences over different candidates, different alternatives. And they come together, they make a vote, and obviously they have to find somebody who is going to win, right? Maybe one person, if it's like a presidential election, or maybe a group of representatives, right? Another example of this is distribution of resources. So we have maybe computational resources, you want access to these computational resources. And the question is, you have your own preferences. How do we distribute these resources among different people? So these type of problems are generally known as cake cutting problems. Right? It has been studied, very well studied in mathematics and computer science for several decades. We can also think about other types of problems like participatory budgeting problems. So these are problems where a group of individuals come together and they have to decide how to spend the budget. Right? So these are examples of a city trying to build something. Maybe city has a budget and they want to decide how to allocate this budget for different projects. Maybe they want to build a library or maybe a swimming pool. What are the decisions that they have to make? Other types of problems actually have been studied for several decades are called matching problems. So these are the problems where you want to match some people to some other things that they also have preferences over. Right? It's a very kind of example of this national residency matching program that is being used to match medical residents to hospitals, right? So hospitals have preferences, these medical residents also have preferences. So the question is, how do you match them together? Of course, there are also other examples like matching organ donors to patients who actually need these donors. And these are problems that are generally called matching. Now, this is kind of like a high level. There are other subfields in collective decision making, but these type of problems actually, even in our today's life, exist everywhere. Right? Thinking about matching you to the best Uber driver or Lyft driver when you're kind of looking for something, right? Or if you think about making decision online, like many open source projects are actually using some sort of voting or preference aggregation to decide what type of the project they want to kind of focus on more, right? And my favorite is gig economy, right? So this is where freelancers have to kind of be matched with requesters and the people who actually want to do the job. And I'm going to talk about one of the examples of the project that we did actually related to gig economy. Okay, so now, all right. Now, collective decision making is one of the core aspects of AI, right? In most of the AI decision making, the solutions, in order to make ethical solutions in AI, we need to kind of address some of the issues, including privacy and individual rights, including fairness and bias, which you're all familiar with, and as well as the value of human judgment, right, into these type of decision making. And these type of problems have been around since Aristotle, and like many different minds have started thinking about how to solve these problems in a better way. So for this talk, I'm going to focus, I'll give you two examples, but then I'm going to focus on one of them more specifically. So I talked about aggregation of preferences. There's also this other idea of distribution of resources or tasks, which is going to be focused more. But I want to give you one example of a kind of recent example of this. So first of all, I think we all agree that preferences matter. I just explained it to you. And this is not just about human decision making, but also if every AI book where you pick it up, they all talk about preferences, right? Because preferences is what makes agents agents. So when I'm going to talk about agents, I really mean any type of agents. Could be humans, could be robots, could be institutions who are making decisions, right? And they all have preferences. Either these are idiosyncratic preferences, or it could be preferences that are based on their needs or capacity and etc. Right? Now, one example, so I think most of you are now familiar with ChatGPT. So if you look at OpenAI website, on their website, they talk about this new technique that is called reinforcement learning from human feedback, right? And this is a technique that ChatGPT and this kind of large language models are using in order to make reward functions for the training of the data on the data set. One of the things on the OpenAI that is mentioned is dealing with human preferences, right? And it mentions that these are actually very complex and subjective tasks that are not fully captured by simple automatic metrics, right? So that's why they have to include human judgment and human preferences and try to somehow align these preferences together. So this is actually right from their website when they talk about how they need to kind of, how ChatGPT or these large language models, at least at OpenAI, works. And one of the things that they mentioned in step 2 is training a reward model based on some labelers, right? So these are human labelers who sit down, they look at these questions or the prompts that were given with the question, and they try to rank the answers, right, that they got. Now they use this ranking in a feedback loop to actually train their model better, right? And this is actually part of aggregating preferences, right? So they need a way to aggregate these preferences to align the responses that ChatGPT or large language models give to more to human responses, so something that we would find like useful and maybe desirable. So this is kind of like an example of how aggregating ranking actually is very important, right? We do have a project on this. I'm not going to talk about this now. Now, another promise that I made is I'm talking about distribution of resources, right? So allocation of resources or tasks. And again, you can think about this from allocating food donations to charities and home shelters to more complex problems like allocating medical resources, right? So vaccine distribution was a big issue in the beginning of COVID. And then there are tons of other examples with the gig economy and all of the needs that they, in order to match users and requesters to one another. Now, again, taking you back to the large language models and foundation models of AI, again, distribution of resources becomes very important in that context as well, right? So one of the very kind of up and coming research areas in machine learning is about collective development of foundation models. And the idea here is that you have clients, you can think about them as agents. Each one of them have their own maybe data that is available to them. So the data could be like samples that they have might be smaller samples or larger samples, right? And they have their own model that they can train, right? At the same time, they may have different type of resources, right? So these are computational resources. So for instance, you may have a large entity like Penn State who's going to say that, you know what, we have a lot of computing power, we don't care, we can train more, right? But then maybe there is a smaller entity who says, you know what, I really cannot afford to train like 1 billion parameter on my model, so I have to use a smaller model to kind of make a decision, right? And I can share it with everybody. But now all of the questions that we talked about kind of it arises again, right? How do we define incentives for these people to actually share the data, the model, the compute they have with one another? And how do we actually make sure that these type of allocations are somehow fair, right? Because you don't want only one entity to do all of the learning and all of the model development, and others would not, right? So again, it's a kind of like one of those examples of how this type of thinking about fairness and fair distribution of resources is actually starts from very humanistic projects until all the way to the projects that we're dealing with today in learning models. Okay. Now, what are the components of collective decision making according to me? Right? So this is not according to anybody, it's according to me. There are several components of collective decision making. One of them is fairness. And apologies if they're too small. Hopefully you can see them. One of them is fairness. The other one is incentives. So we just talked about how do we incentivize people to participate. The other, an important one is efficiency. Obviously, when we are making decisions, we want to make sure that decision has some sort of efficiency. Elicitation of preferences is a big problem. Explainability of this, which I'm going to touch upon a little bit at the end. Human judgment and ethics. I'm going to mainly focus on fairness, but along the way, I'm going to talk about human judgment a little bit, incentives a little bit, and so on. Okay, now let's kind of focus on fairness. What is fairness? What are the main pillars of fairness? Again, according to me, right? This is not according to anybody. I don't have any sources to ask here, right? One is the axioms of fairness. What I mean by axioms of fairness is how do we define fairness, right? So maybe many of you are thinking about, yeah, we think fairness is cool. We want to make fair decisions, but how do we define them to begin with, right? There are a variety of notions of fairness that has been developed from philosophical perspectives all the way to very computational perspectives, right? Some of them we're going to talk about. Some of them care about envy-freeness. Some of them talk about fair share, equitability, and so on and so forth, right? And the impact of endowment. So there are all different ways that we can define these axioms of fairness. Okay, is that enough? Of course not. That's why we have computer scientists and AI researchers, because in order to achieve them, you need algorithms, right? So we need to have this algorithmic way of achieving this, right? How do we achieve fairness? How do we compute fair solutions? How do we find approximation that are computable? And how do we deal with compatibility issues? Sometimes some of these axioms of fairness are not compatible with, let's say, axioms of efficiency, right? And there are many examples of that. Right? And lastly, is the alignment with human judgment. Right? So this is something that I really care about, is that how do we align these axioms and algorithms with how humans actually value an outcome or see a solution, right? How do we perceive it? What are the ethical issues there? And how can we use this to maybe define better axioms? So this whole talk, I'm going to talk about these three different things. Good. Okay. So as I promised, I'm going to mainly talk about distribution of resources, services, or tasks. And I'm going to use something that, of course, many of you are familiar with here as computer scientists, is abstraction, right? We love abstraction because obviously we're not smart enough to solve the big problems, so we have to solve big and tiny problems, right? So that's what we do, abstraction. Now, let me kind of start with a very simple model. So my model is as follows. So I have a set of items. These are indivisible items, right? I just used musical instruments. Why not? They look nice and I like music. So, and you have agents, right? So you have maybe two agents here, right? Two agents. And you have M goods, right? Goods or items. And I'm going to talk about this, that sometimes we also think about bats, which we're going to get into, right? These agents have preferences over these goods, right? So these are values that they assign, right? This is not a purchase value. It's just a value, right? So somebody really likes to play the piano, is going to say my value for getting the piano is 56. That's how happy I'm going to get, right? By having the piano. But maybe the other agent's going to say, you know what, I don't want this, right? My value for that is low. It's not, right? And of course, if you give me a set of these items, bundle of these items, then my valuation is usually additive, right? So that's an assumption that is not always necessary, but it's an assumption that we make just to make our life easier and write proofs. Right? Really, it's just make our life a little bit easier. So essentially, if I give agent 2 these 3 items, the valuation for this agent is going to be 45, the sum of its components. Right? It's simplified. We don't have to be like that. Sometimes we have submodular or supermodular valuation. One of the examples I'm going to talk about at the end is supermodular, so you can ask me about that. But for most of the talk, we're going to talk about these type of additive valuations. Okay, now, how do we compute a fair distribution of resources? Imagine this was my problem. I'm going to give these instruments to these 2 agents. How do I find a fair solution? Right? Now, based on those preferences and valuations, of course, the first question that I already told you is that what is a fair solution? And this has been like studied for many, many decades, starting from Steinhaus, who talked about proportionality. Right? And the idea behind proportionality is that I'm going to, if there are these 3 items, I'm going to say that, well, I look at the value that you have for everything. And if you get 1/n, if there are n agents, of that value, then I'm saying this is fair. This is a fair share that you have. So in this case, you can kind of check this yourself. I think you can do simple math to see that this would be a fair share. If you look at agent 2's value is 50, and he gets even more than 50. So it's a fair share. So that's one type of axioms of fairness, and I'm going to talk about another version of that as well. It's a little bit more advanced version, but this is just for start. Another axiom of fairness is more of a comparison-based axiom. It's the idea of if I have something and somebody else has something else, I should not value what they have more than what I have. Right? This is called envy freeness. Obviously, you are familiar with envy. This is envy freeness. So in this case, you can check to see that this allocation is envy free, right? Now, why? Because let's say agent 1 is looking at agent 2's items and says, okay, from my perspective, agent 2's bundle is only valued at 44, which is less than the value that I did, right? So I am not envious of the other agent. And similarly, agent 2 is not envious of agent. Okay. Now we learned some basic stuff. Now the real truth is that envy freeness or proportionality are not possible. So it's not, we cannot satisfy it all the time. And you can see, as it's a very simple example. Imagine there's a house and there's a husband and wife, and they don't want to sell the house. They have to somehow decide how to split the house. Now, of course, one person is going to get the house. The other person is going to be very upset. It's going to be envious, right? Now they can cut the house like this in half. The value of the house goes down. By the way, this is a real picture of an American artist who actually spent, I think, more than a year cutting a house perfectly in the middle. It's an art piece. So, I'm not making this up. Okay, how do we deal with situations like that? I just told you 2 nice axioms. They don't work. How do we do? Of course, we do some sort of approximation, right? So either we can do some probabilistic approximation of fairness, right? What if I flip a coin, right? Or what if I kind of make sure that both of you participate in some sort of a lottery to get the item, right? So that's one type of kind of brand of or direction of research that I have done over the past several years, and I'm not going to talk about those now, but I'm going to talk about another type of approximations that are more deterministic. So how do we deterministically approximate fairness? Okay, the first idea, well, one of the ideas that we had is that why don't we use this kind of information asymmetry between the agents? Now, let me tell you why we want to do that. So there is one notion of fairness called envy freeness up to 1, right? This has been like a very popularized notion in the past, let's say, decade. And there are lots of papers on this. So the idea behind this and freeness, it says, okay, it's fine, you can be envious, but your envy would be eliminated by the removal of only 1 item. So my envy is only as much as 1 item, right? So if Lisa there gets like multiple items, I would say, you know what, if she didn't have the diamond ring, I would be happy. So, and this type of fairness can actually be satisfied, right? It always exists, and we have good algorithms to find it, right? And one of the very simple algorithm is a round robin algorithm. This is exactly what it does. So agents come, pick up the value, pick up whatever item they want 1 by 1, and then they just repeat this, right? Now you can check to see that in this case, if agent 1, I'm using this wrongly every time. If agent 3 is envy of 1, so agent 3 can be agent 3 can be envious of agent 1, but it's going to say that, well, if agent 1 didn't have the guitar, maybe I would not have it. So the envy is limited up to 1 item, not more, right? And that is true even if you have thousands of items. Right? So that's the beauty of this. Right? And you can check the same thing for all the other. So this is a it's a notion that has been studied very well in the literature, but it has issues, right? So one of the issues is that if you actually get to remove items, you will have examples like this that all of the items are going to be removed, so nobody gets it. Not good. Right? The other issue is that if you think about the hypothetical removal, well, it's hypothetical, right? It doesn't really kind of gets rid of envy. You still have envy, right? So there are other ways of approximation that exist that use some sort of information withholding in order to achieve envy-free, right? And the idea there is that, well, in real life applications, there's tons of things you can know. You cannot have information about everything. So maybe we will just not give you information, right? So this is called epistemic envy-free. So you only know about yourself. Maybe you can make some guesses, but those guesses are really envious in expectation, right? So we thought about this and we realized that maybe this is not good because this kind of goes against transparency. You want to be transparent when you're making decisions. So how do we do that? We can maybe withhold information about specific items, right? So there are some items, a subset of items that we're going to say that we're going to hide these items. So the agents who receive these items are actually enjoying the items, but the rest of the people don't see them. Right? And if you think about some large applications, maybe it makes sense, right? So they're not going to be very envious because you don't know what happened to that data, right? Maybe there are lots of items you receive them, maybe you don't know. So this is kind of a better approximation. By the way, you can hide everything, right? That's not very nice. So the question is, how many items do we need to hide? Right? I mean, if you have thousands of items, you don't want to hide all of them. What is the best guarantee that we can achieve? It turns out we only need to hide n-1 items, right? N being the number of agents, right? And we can compute this in polynomial time, and we can even achieve efficiency with that, right? Something that I didn't talk about is the idea of Pareto optimality, or Pareto efficiency. So Pareto optimality essentially says that we don't want items to be allocated in such a way that later on people want to kind of swap their bundles. Right, so I'll go to Justin and say, "Hey, we want to kind of change," and he's going to say, "Yeah, I'm going to say, yeah, it's not good." But it goes against economic efficiency. So we can achieve this n-1, even if you have thousands of goods. N-1 is enough. Now you might ask, "Well, what about is that the lowest amount that we need to hide?" It turns out that that problem is actually hard, right? In the sense of computationally, it's intractable. We cannot find the optimal number of items. Right? So we cannot go below n-1 without some computational difficulty. Okay, now we wanted to also experimentally see what happens. So we actually had access to data that people actually use. So these are real data from real people who had instances of fair division problems. And we had access to these, and we kind of looked at in these type of data of real people, we have 2.2 thousand instances. In this type of data, how many items do we actually need to hide? And it turns out that only few goods need to be hidden, right? Yet generally speaking, it was less than 3 in all of those examples. So it looks like it's kind of not bad, and perhaps people kind of like this more, right? Now, I haven't told you whether people actually like this more or not, but wait for that. That's going to come at the end.
Can you tell us a little bit more about that splitted data set? What, one or two examples of the context of the?
Yeah, so the splitted data set, Split is a website that you can use. Actually, it's a website that they have a different type of applications. One of them is division of like resources like this. Some of them are division of rent. So let's say you want to decide who gets what room and who pays if you are sharing room. And people can actually go and use this website, right? So there are a bunch of people who have been there, many people, 2.2, and they're solving problems. And it turns out that some of the problems they're solving is kind of more about, okay, how do we divide inheritance? So we have stuff, maybe a parent died and they want to decide what to do. And the website actually uses these provable algorithms, to give provable guarantees on fairness to these people.
Oh, so it's a tool that people, it's a decision.
It's a decision-making
Yeah.
tool. Exactly. It's a decision-making.
Right.
Yes. Now, I'm going to come back to this and talk about how people actually think about this type of fairness. Justin,
And then they follow up and then ask them afterwards, did you like this?
no. This is just algorithmically.
No, but the data sounds like you actually have some extra data about whether people like what we
This is not about people's liking at all. It has nothing to do. It's just about how much we can do in order to hide. It is completely mathematical, right? Has nothing to do with what people perceive to be fair. I'm going to talk about the perception towards the end. Actually, on the same. Maybe I should have put it here. I'll put it here later. Makes sense. Yeah. But at the end.
So we're paused. So my question is about we're hiding one good, and that good has an unbounded value, right? Like let's suppose it's the mythical $1 trillion bill of the Fed infringement. How do we kind of deal with that?
Yeah.
Because all the examples we've seen so far, all the values are kind of the same range.
That's a very good question. It's actually a question that our reviewers also ask. True, we cannot deal with it. It's if there's one good, it's very highly valued. You can say, well, maybe there are different ways in practice how you want to deal with it, right? So I think theoretically we want to achieve some approximation, but in practice, you can just not allocate that good. Or you can just select that one good and maybe randomly allocate it. Or maybe you can sell it and somehow now you have money, which is divisible, now allocate that. So there are different ways practically you can deal with it. But from a theoretical perspective, you're absolutely right. Yeah, if you have like a massive diamond in it, whatever else you give them people.
So the ethics of hiding that are challenging, right?
That's right. Yeah.
The side comes to mind.
I have a follow-up to John's question. So what if there's a clear hierarchy in the valuation of the goods? So you have the example of the instruments.
Mhm.
And of course, someone values the guitar more, someone values the piano more. What if the hierarchy of valuations is constant across agents?
Yes, very good question. So the question that Ramit is asking,
Yeah.
Yes, you teach me know how to do this. Is that what happens if the valuations are somehow hierarchical? Like, so people agree on the order of this. So our solution, it's actually a very good question. So what I'm talking about here applies to that as well, right? Because we're solving it for a general case. So it's solved. However, you're absolutely right. In some of the things we're going to talk about later, we actually use that, right? We have techniques that we use that. And sometimes it makes the problem easier when people agree, right? So they have some objective view about maybe the ranking or the valuation of items and all that. It usually makes the problem easier. Whatever we talk about so far, we've talked about actually applies to a general case. Okay, I have a lot more to cover, so let me go a little bit.
Yeah.
And it's okay if I don't cover all. Now, one question that you might ask is that, well, you talked about goods, but what about chores, or what we call bads, right? So goods are good because they give you positive utilities. Chores are bad, things you don't want to do, right? My favorite, I mean, you can think about household chores around the house, like who feeds the cat or clean the litter, problem we always have, or washing the dishes, or taking the dog out, things like that. Like, these are chores, maybe necessarily not something that you want to do. You don't enjoy it, but you have to do it, right? And of course, chores, the one thing about chores is that chores are not disposable. Goods are, right? So if you have a diamond, just throw it out. Who cares, right? I mean, we can, but you can just do that. It's disposable, right? Whereas chores need to be done, right? My favorite example of this is the collective ownership responsibilities when it comes to, let's say, nuclear waste or climate change or gas emission. So these are chores. Like every country, every state, every city has responsibility. Of course, there's going to be some budget, some negative thing that they have to put from their budget to solve that problem, right? But the question is, who has to do how much, right? And here, we also care about that. It's not just about goods, but it's also about chores. Now, in these type of problems, it turns out that achieving fairness is actually much more difficult than the case of goods, right? And one of the properties that I mentioned before, satisfying this notion of EF1 and PO, is actually becomes more difficult when we're talking about chores, right? Mathematically and algorithmically, right? There are tons of new open problems there. The same techniques do not apply, right? From goods to chores. Now, I'll give you like an example. So imagine you have these household chores that you want to do, like taking the garbage out, cleaning the floors, or maybe do the laundry. And then, as you can see, the valuations are all negative, right? So what we can do, yes, you can kind of satisfy, you can give the agents to do in a round robin fashion, they can still pick up some of these items, right? And do it. And that is still EF1. The problem, as you can see conceptually, is that in this case, if you want to kind of eliminate one of the chores, so let's say eliminate the envy of agent 2 and agent 3 towards agent 1, then we have to remove their chores, right? Because we cannot remove the other person's chores, because that means they're going to do nothing. So you have to remove their chores, which means that now after removal of that chore, agent 1 is going to be more envious, right? Because now the other 2 are not going to do anything, and agent 1 is not going to do anything, right? So that actually makes the problem conceptually more difficult to solve. And as I mentioned, theoretically and algorithmically, it's also more difficult to solve, right? So one idea is to, well, let's use information asymmetry. Now, previously, we were able to hide some goods. Here, hiding a chore just is beneficial, right? It actually makes the problem worse, right? You want to make sure that people see what other people are doing. So we thought about creating some sort of information asymmetry by introducing what we call dubious chores, right? So these are chores that we kind of replicate. Well, it looks like this agent 1 is going to do this chore, but it's really done. Right? The agent needs to only do laundry once, not twice. Right? So this is a dubious chore. And a similar question you can ask, how many of these dubious chores do I have to add? Right? Worst case, you have to add, what's it, n times m, one of them? Well, that's an all of that, right? So you don't want to add as many of them, but it turns out actually you only need to add 2n minus 2 dubious chores, right? To achieve complete NV3, right? And you can do that with Pareto efficiency, right? Although now you no longer can compute that solution in polynomial time, which is another thing. I'm not going to get into the details of that, right? So as you can see, for the case of goods, we needed to hide only n minus 1. Here, we can do 2n minus 2. Question is, can we do better? Maybe. Can we show it or prove it? We don't know. These are open problems. These are currently open problems that nobody knows how to solve. Okay. So I promised you to talk about another notion of fairness. And this notion is very similar to what I talked about proportionality, right? So if you get 1/n of the value of the all items, be happy, right? Now, of course, when we're talking about indivisible items, proportionality doesn't really make sense. It's not helpful because we showed that it doesn't always exist. So we're going to look at another notion called maximum fair share, right? It's a very similar, it's kind of an extension of this proportionality. The idea here is the following. So the mathematical formula, for those of you who are interested, you can read it, but the idea behind it is the following. I can ask an agent, say, hey, Carleen, if you were to distribute these items, knowing that you are the last person and put them into n bundles, knowing that you would be the last person that you're going to choose, how do you distribute? Right? And Carleen is going to distribute them in this way. And I can go to the other agents and ask the same question from them, and maybe they have different. Right? So this is kind of the idea of you partition, but you choose last. So what you try to do, you try to maximize the worst bundle for yourself. Right? So that's the idea of maximum. Right? It's actually a very well-studied notion, which actually works in the indivisible case. It turns out doesn't always exist. Same problem. So we don't have this fairness axiom, and there are many multiplicative approximation of that exists. Right? So they tell you that you're going to get 3/4 of your fair share, not all of it. Right? The problem with these approximations generally is that they're not robust to small changes, right, to valuation. So you might have different preferences. Maybe this is your preferences, but maybe you're not very accurate, right? Maybe you say that, I think my value for guitar is 10 for the guitar, but I don't know, maybe it's 12. So maybe there's a little bit of like noise in your valuation. It's very difficult to elicit these valuations correctly. In fact, it's difficult for humans to think about it, right? Or maybe another agent says, well, you know what? Maybe my valuation is not 4, maybe it's 8, right? As long as it's kind of the ranking is the same, going back to Ramit's question, then it's fine. You can have some wiggle room in your valuation. So it turns out this other approximations actually fail miserably when we have systems like this. So we have to come up with better type of approximations. Right? Now, there are 2 ways we can deal with this. One, what if we remove some agents? Would that help? Right? Or what if we add some dummy agents? Would that help? You think about that. Now, what does it mean? I'm going to go very quickly about this. So we looked at this idea of removing agents, saying that, well, we want to make sure that alpha fraction of agents receive their beta fraction of their MMS. Now, when beta is 1, they receive the complete fair share. Right? We looked at this problem and we were able to show that at least you can only remove 1 agent, and there is a polynomial time algorithm that gives you this approximation, right? This approximation of beta. It's not very good. For small instances, it works. For large instances, it's not a very good approximation. But the good news is that we can always give 2/3 of their agents their MMS value, their fair share. And in that paper, we showed that you can do it polynomially if you have number of agents is less than limit, right? Which is kind of tricky thing. And I'll tell you that later we showed that we developed a new algorithm that can actually do this polynomial term for any number of agents. I'm not going to go through this, but the experiments, we ran some simulations. These are simulation experiments based on synthetic data. And we show that, in fact, the algorithm that we have, most cases, we have more than 85% of the agents receiving their full MMS. Right? So again, these are not real data. These are synthetic data. Right? Now, as I mentioned, we talked about what if we introduce dummy agents, right? And you can do that. So I can come back to Carlene and say, you know what? I told you there are 3 agents, and what is your MMS value? But now I'm going to tell you there are 4 agents. Imagine there's an extra agent. What is going to happen is that your MMS value, fair share, is going to go down. Right? It's going to weakly go down. But stay the same, but can never go up. So can I now maybe satisfy this type of approximation? So that's the question that led us to this generalization of, well, you can generalize it. You can say, can I give you L out of D approximation? So imagine that you're getting, instead of 1 last item, you're going to get L bundles at the end, right? So we can kind of extend this as much as we want. And it turns out that we can do this and we can develop an algorithm that gives you 3n/2. So it really means that you can add 50% more dummy agents. It's not very good, but at least we can compute it in polynomial time, right? Now, there is a gap between exact n plus 1 and 3n divided by 2, which not much work has been done. We don't know much. Okay. Now, Cindy is asking, what about chores? You didn't ask, but yeah. What about chores? So it turns out, again, chores needs their own techniques. The same techniques for goods don't apply for chores, but we can actually do better approximation. By the way, the key about chores is that for goods, I can give you a good, as long as it gives you a fair share, you're happy, you leave, right? The problem is that I might not have enough goods, right, to give everybody. Chores is the other way around. If I give you 1 chore, maybe I can give you more chores before you get unhappy, right? So I have to pack as many as I can, right? Right below you get unhappy. So that's kind of the tricky thing about between chores and goods. But it turns out that we can actually achieve some good order approximations for chores. Right? Again, I'm not going to go into the details. I'm happy to talk to you about this. How much time do I have? Oh, good. Okay. So I want to move you now. As I said, I'm giving you like an overview of these projects that we have been talking about. Now you might say, well, Cindy is coming back and asking me, what about goods and chores? What if you have both? Right? Does it make sense? Of course it makes sense. So some of you come to this talk, and this talk is so valuable for you, right? Here. Some of you, Justin says value for this talk is 100. Somebody says maybe 0, the guy who left, right? But all of you are positive. Right? And then there might be some chores, right? Maybe some stuff that you don't want, right? Maybe you don't want to do it. And the question is, and there's some stuff in between that are subjective, right? So maybe walking the dog, it can be a subjective thing, right? I love taking the dog out, like playing with the dogs and all that, but maybe somebody else here is allergic. You don't want to do it. You can't do it. So you have negative values. And this type of problems, by the way, going back to this kind of compute and resource sharing models or foundation models, you can think about this, right? You can think about models that you're sharing with everybody else as a good. So people want to have new models, new data, but the learning tasks or training tasks are negative. So you can think about this as well. My favorite example is reviewing papers. So many of you are going to review papers. So if you have a very cool up and coming paper on some advanced AI model, everybody wants to read it. Everybody is very positive about it. Or maybe there's a really horribly written paper. Nobody wants to read it. Right? There's negative, but somebody has to review it anyway, right? And then there could be some papers in between, right? Maybe there's a game theory paper I'm really interested in reading, and there's an HCI paper that somebody else is interested in, right? But maybe, I mean, I'm not negative, but I'm not super positive about it either, right? And maybe somebody says, you know, I hate game theory. Never going to do this in my life. Fine. Now, how do we do this? How do we deal with goods and chores? So we looked at this, and we have to kind of change a little bit the way that we model preferences. Now we're going to think about preferences as importance ordering over these items, right? And here, what we're going to say is that I really care about this one item. This is a positive thing. So having this item, I don't care about the rest of it, right? Conditioned on that, I really dislike the second item. Right? So maybe walking the dog, right? I cannot walk the dog, right? It's the most important thing for me is not to do that if I get O1. So it's a conditional type of preferences you can think about. And this actually gives you some sort of a lexicographic extension over all possible preferences that you can have. And just for the ease of showing this, I'm going to use these colors, right? So, and O1, O2, O3, they have 3 items and they're different colors. So if there's blue, it's a good for that agent. If it is red, it's not it's a chore for that. Now, what can we do here? Well, before even telling you what we can do here, I'm going to talk about even a stronger notion. Remember, we talked about EF1. And I mentioned, well, you can hypothetically remove one item. So there exists an item that you can remove. I can make this stronger. I can say for any item that you remove. But this doesn't say exists an item. It says any item. So if you have a diamond and a pair of shoes or Kit Kat, any of those, after removal of that, you should become NB. It's a much, much stronger notion than EF1. And of course, because we have chores, you should be able to remove any of your own chore as well. So any of the chores or any of the goods. Question is, do these EFX allocations exist and can we compute them? Right. So this is actually has been an open problem for a long, long time in my field, and people have been looking at it for goods only or chores only settings, right? Not even mixtures, just goods or just chores. It turns out we don't have an answer to this. We don't know whether it exists or not, right? We cannot find a counterexample. People have done millions of simulations, and we cannot find an algorithm to even check whether one exists or not. So it's a big open problem. What we were able to show is that when you're dealing with mixtures, even under this restricted setting of importance ordering or lexicographic orderings, EFX doesn't exist, right? And it doesn't exist even if you have objective preferences. So meaning that everybody agrees on what is a good and what is a true, right? So it doesn't exist, but that's what we settled. And if you want to check whether an instance has an EFX solution, that problem is there. With computationally intractable, we cannot find an algorithm to solve it. And this, of course, extends to additive valuations as well. We also had positive results, right? So we kind of looked at positive results and said, okay, what are the conditions where we can actually satisfy this notion of fairness? So we have some positives. I don't want to go into the details of those, but if you're interested, I'm happy to talk to you. So this was a paper that kind of we submitted to each guy last year. Got it. Now, I'm gonna end by 2 things. So one is talking about one application that I really like, this project a lot, and it's kind of application of what we learned about fairness. Of course, I haven't touched upon all of the notions. I've touched about maybe 3 or 4 notions of fairness. There are many more that we have studied and people are studying. But there are 2 things I want to talk about. One of them is fairness on graph. So this is kind of, I'm going to start this with an example. So imagine you're 3 friends, right? And you're going to distribute papers in the morning. So these are newspapers. You have to go to each house and you have to give this. And this is kind of like an example of a very standard suburban area in North America. Right? So you have to like take your bikes and go to these different houses and give them newspapers. Right? So deliver these newspapers to these different houses. Right? So there's 3 of you. Now, what we can do, first of all, we can model this as a graph, right? You can already see the graph, but I'm going to get rid of the map. Now we can see the graph. So now we have a graph of the path that you can take. And you want to kind of take this, right? And of course, there is a hub. This is a starting point. So you all live in the same house. From there, every morning, you have to go and distribute these papers, right? How do we do that so that it's fair? Okay, so we can look at the first one, right? So maybe we can make this decision. So the blue guy is going to go and visit all of these houses here. And then the green guy is going to visit these ones, and the red guy is going to visit the other one. So this is the blue one, red guy, and the green, right? This seems very unfair, right? Looks like blue guy is the one doing everything. Very not good. So we're not very happy with this solution. It's a very unfair solution. Now let's make it maybe fair, right? So everybody goes to every other house. Now the blue guy has to travel this much. Green guy has to travel this much. And the red has to travel this much. It's a very inefficient solution. You ended up going all the way through the map, all of you. Why did you do that? It feels a little bit counterintuitive. Why would you do that? But it is fair, right? I mean, the question is, what can we do, right? And this type of problems actually exist, as I mentioned, in the gig economy. You think about how Amazon, what's it called? The Amazon freelancers. No, there's another term for Amazon. Sorry?
Oh, the mechanical turk?
No. The people who kind of distribute your Amazon Flex. Yes, exactly. So people on Amazon Flex can go and then they get this shipping, and they have to go and deliver these shipping orders, right? Companies like postal services, FedEx, Grubhub, Uber Eats, all of these, and even like charities like Meals on Wheels have to deal with these questions, right? You cannot just send one person. You also don't want to kind of be very inefficient. You want to be fair toward the people who work. You also want to be efficient, right? In the sense that you don't want to send repeats, right? So maybe this is a better solution, right here. It's not necessarily the most efficient one, and it's not necessarily the fairest, right? But can we find a solution like this? So that was our big question. If you're dealing with any graph, right, that is given. We focused on trees, right? I'll tell you there's a technicality problem with cyclic graphs, but let's assume it. And we were able to show that, yes, you can actually achieve some of this. So some of the fairness problems actually remain NP hard, which means that computationally, we show that you cannot compute them in polynomial time. But there are some solution of MMS and PO you can always satisfy. It always exists in this section. You can always get a fair solution, fair with MMS, and efficient solution, right? Computing this solution is actually quite difficult. So we have a way to compute the Pareto frontier of the solution. So these are all of the Pareto optimal solutions, all the solutions that are efficient. And then among those, we can identify a solution that is MMS. So we have an algorithm, which is not polynomial, it's XP, but it can find an MMS and PO solution. And we kind of ran some experiments, again, syntactic data, syntactic graphs, right? These are not real data. And we were able to show that the price of fairness means that efficiency loss is not actually that much. So it's not bad. You can actually find a fair and efficient solution. Okay. Good. I have 4 minutes. I want to end at 1 so that I can take questions. I want to talk about one thing I promised to talk about. It's the alignment with human value judgment. So this is kind of a newish project that I have been working on with some collaborators and some students who are here actually. And we're thinking about, okay, we talked about all of these algorithmic and axiomatic ways of defining fairness, but what is fair? How do people perceive that? If I go and really implement this, maybe people don't, right? Or which one people don't. There are tons of these fairness axioms and algorithms, and now approximations on top of them, because not only we have these axioms themselves, but also approximations. Which one of these should I use, right? Among this whole fairness zoo, think about. So we started by looking at, now going back to the first problem that I looked at, right? Thinking about hiding some good, remember that? With the counterfactuals and saying that, well, what if the other person didn't have that? So we ran this kind of relatively large experiment. Maybe I shouldn't say that. We ran an experiment on Amazon Mechanical Turk. And the experiment was carefully designed to compare these two approximations of fairness. EF1, remember the one that the hypothetical removal, and the hiding one. So we created these kind of instances, very careful instances, where with a scenario of a pirate. So imagine you're pirates, you find some treasures, because obviously you want to make sure that and these are the treasures that you found, and you want to distribute them, right? So and you got this, for instance, this was your reward, the treasure that the captain gave you, let's say Captain Sparrow, and would you like it or not, right? So we didn't really ask, would you like it or not? We said, well, these are the rewards that the rest of the people got. Would you like to swap or not? Right? And we use this swap measure as an indirect way of see whether they envy the other agents or not. Right? And we were able to show that, in fact, the hiding notions of fairness perceived to be fairer than the EF1 notions, the ones that come with counterfactual. Right? Now, I'm not making any claims. So we did a lot of other studies and analysis of the data in small instances, larger instances, and all of that. I don't know the reason. One justification behind that, I mentioned that. So one justification behind that, it could be that people have some bounded rationality, right? Or what Daniel Kahneman says, kind of what you see is all there is. Right? So this is kind of the idea of, because you don't know who got these items, maybe you don't really think of it. Maybe it's fine, right? So maybe people are kind of, we can use this to design better fairness axioms. Right? So at least it shows that in practice, one very, very controlled study by the way. People seem to be more happy or happier with this hiding or information withholding type fairness notions, right? Than the one that I get. Now, this actually brings me to this higher level idea of how should we deal with the axioms of fairness. I started with this, and I want to kind of almost go to the end with this. My idea about axioms is that axioms of fairness must be explainable, right? So they have to explain the solution. They should be aligned with societal and cognitive values, right? There are many, many cognitive values that we didn't talk about. And we do have actually some projects going on right now on those topics. Be accepted by people, right? By stakeholders, and be verifiable. So this is another issue. I don't want to get into the detail of it, but this is another issue of how do I make sure, as a user of a system, how do I make sure that the system is actually fair? Just you telling me that this is fair may not be good. So I have to enable ways for you, or create ways for you, so that you can test the system, or can make sure you verify it yourself, at least to the extent that is possible. I wrote a paper on this, which I'm going to present at AAAI, and the paper is available. This is more of a high-level idea on my website. You can read it. I'm happy to chat to you about this. One of the parts of this is explainability, right? So it's kind of how it relates to explainability in AI, which generally is kind of, a lot of research in machine learning thinks about this explainability as transparency of the mechanics of the algorithms, right? So, but the way that I'm looking at explainability is really about how do you explain a solution to users, right? And that brings a lot of other new things, as we talked about, right? New things about how do you elicit these preferences from people, and how do you maybe use visualizations or some sort of interaction with the users so that you can explain the solution. right? And there is a lot of research showing that we have to, like, if you want people to feel fair, you have to like improve maybe a little bit of their algorithmic literacy, right? And algorithmic thinking. And the way that we are also showing them things actually matters, right? And I'm going to talk about these two projects that we have. One of them is called, it's a very long project called matchu.ai. And the idea of this is that there are some, it's a tool, right? So there are tools, there are some algorithms that we have implemented in this website. So what you can do, you can check, you can see which one actually will solve your problem or applies. You can go to it and you can add your data to it and it will solve the problem for you, right? Not only that, it visualizes the steps of the algorithm so that you can check back, you can go back and see what is happening, right, in the solution. A newer project that we started with actually two of the undergrads here, this project started like maybe a year ago. We call it Match Explain, right? So maybe it's catchy, maybe it's not, I don't know. But the idea here is that we want to go even beyond just showing you how the algorithm works. We want to be able to show you exactly what your data looks like, because that matters. I cannot just give you the output and assume that you're going to accept it if you don't really understand your input, even though you came up with it, right? So I want to be able to show you and analyze the input for you and tell you exactly what your input looks like. So we are focused on matching problems or allocation problems, but how your input looks like. And then we are going to generate a set of solutions for you, right? And you can choose whichever solution. As I mentioned, some of these properties are incompatible. So we can choose a set of solutions and show it to you, and you can select them, right? You can say, well, maybe I would prefer this, even though I know it creates a little bit of envy for these two agents, but I'm happier with it. And that's the idea behind it. And that kind of gives you a solution and you can kind of interact with the solution. The very, very ambitious idea that I have is that at some point we should be able to allow you to even slightly change the input and see exactly what the output, how the output is going, right? But there's a lot of questions, right? Even computationally, some of those questions are not very solvable. So I want to end by, I have a lot of collaborators that I'm very lucky to work with, but even better than that, I have awesome students. These are all the students, former, current students who have been in my lab and helped in some of these projects. And these are undergrads, and that's it. If you have questions, I'm happy to take questions, and I'm happy to chat with you about any of the things, if it any way relates to your work. If it doesn't relate to your work, but you just want to chat, I'm happy to do that too.
Great, thank you. Run the microphone. Questions? Any questions?
My questions, sort of two. The first one is, to what extent have time varying preferences been studied in the literature? And then two is about observability of preferences. Part of the reason I describe that is that, you know, in my class where we talk about policy-based versus value-based, I sort of say that policy-based is more aligned with human thinking. When I get up in the morning, I don't think my value for eggs is 10, my value for eggs is 15, my cereal is 5, therefore eggs. And so we don't actually externalize the preferences in this way. So oftentimes we have to solve problems where we don't know. Maybe I'll tell you that I like eggs, but I won't say that. So those are my two questions. Thank you.
Yeah, thank you. The first question is about time varying. So there are some work looking at what happens when preferences change over time. And they're looking at how we have to redefine fairness in those cases, right? So sometimes you have to define fairness over a period of time. Maybe you can satisfy fairness if you know what the planning horizon is going to be. But if you don't know the planning horizon, then you have to make sure that the problem becomes harder because not only you want every step to be fair, but you want the sequence of steps to also be fair. So there's some research in the field that talks about the preferences changing over time. I think I had a paper back in the day at AAA, and I remember one of the reviewers wrote 3-page review saying that preferences don't change, and I really believe in that. And that was the first rejection.
Preferences.
Yeah, so-
Not only do they not change, everybody has the same.
Exactly. So there is some research, but not as much because the problem becomes very difficult from the algorithm perspective. The second question was from about observability of preferences or
Yes.
the outcomes.
Preferences.
Preferences. Not much work has been done in that. Most of the work that at least I'm aware of, the assumption is that we have some way of either the preferences are available, we can just kind of look at them or ask or elicit them, or we can learn, right? Now there is a lot of literature on how to learn preferences or how to elicit preferences. The illustration is also a difficult thing. So something I didn't talk about at all on purpose is that you may not know what's your value for tea versus coffee. So there is a lot of like literature about how to elicit those preferences. Not much more has been done. Okay. Tommy?
So my question goes to the example you shared about chores. Is there any notion of bringing in competence as well as in between, so preference to deciding the allocation of chores? Like, I don't want to take the dog out, but I'm really good at it. Whereas someone really wants to take the dog out, but loses the dog.
Yeah. I love that a lot. Yeah, it's a very good question. I deal with that problem in my life. Usually people ask me to do stuff. One of them is here that I really don't want to do it. But yeah, so no, right? In the way that you can definitely model this type of competency into the system. You can also like think about cases where it is already modeled as a preference. So when we talk about preferences, we're not always just talking about, okay, this is your idiosyncratic way of thinking about the value. You can model it however you want, right? And there is a large number of like massive literature on preference model, right? User model, preference model. I haven't seen any work that looks at them separately from like, okay, it uses competence, but then they don't have much to do, right? I mean, we have this problem with students. Students who really want to do something, but they don't have the competence to do it. Sometimes they can, hopefully they can do it that way. It's a very interesting avenue. I haven't seen.
So in a somewhat similar vein to that question, I have a question about two potential extensions of the problem. One is the consideration of interactions between agents, especially in the example of inheritance. Two siblings hate each other. What they really care about in this problem is that the other one doesn't seem to be making out better than them, but they'll both be willing to take a suboptimal solution otherwise. So I don't know if there's anything in that.
There is. So it's a very good question. You can model these type of. I mean, I've seen these problems to be modeled in auctions, which is a type of resource allocation. So there are companies, especially larger companies, that are competing with smaller companies. Let's say for a spectrum auction. So these are the auctions for the wireless bandwidth, right? That the government, FCC, actually sells. And there is actually behavior of spitefulness. Like they try to kind of say, hey, don't bid for this because if you do, I'm bigger. I know how to deal with you later. There is some work on auctions in the cases where we don't have money. You can model these as externalities. So you might have positive or negative externalities. Even adding to your question is that maybe the value I get from maybe coming to the project or coming to this seminar room goes higher if I'm coming with Justin, right? If I'm coming with my friends, right? But if I'm alone, maybe I have lesser value. So this is kind of type of externalities that we can impose, positive or negative external. There is some work, not much.
The other one that I'm thinking about is it seems like the rows here, they may have an arbitrary scale where, for example, one person You may actually have fewer preferences than someone else. And yet that is basically a latent variable that you don't know. And that could imagine, you could imagine that in the app, like that's basically an unmeasured confounder that might modify the optimality of the solution.
Absolutely. So what some of the solution concepts that I talked about are scale free, right? So you can easily normalize all the valuations and you're done. Nothing will change, right? Some of the solutions aren't. And yes, that's important. When we talked about MMS, maximum share, that's a scale free axiom. Right? So you can just scale it up, scale it down. Actually, one of the techniques we use to find these, to develop algorithms to solve them is to first scale them so that they all look alike, right? At least they're summing up to the same value. And then after that scaling, what you can do some, which we call it normalization. What you can even do further, you can order the instances, right? So you can say, assume that I change the label so that everybody agrees on the ordering of the items, which it may not be true. But that actually helps us here to solve the problem. So we are making the problem specifically harder, solve it, then bring it back to the easier case, right? And show that it also says.
The information may not actually be in the preference state. Right? You can imagine a situation in which someone just wants to say that they hate all of these chores, minus 100, but that's just not there. It's unmeasured.
The spoiled child.
Yeah, the spoiled child, or like I want all of this.
Yeah, but if you normalize it, then essentially you're saying that you like or hate at the same time. So it doesn't matter for you which one you get. So the normalization there, as I said, not everything we talked about is scale free. Some of them are, and you can normalize them and scale them however you want. But in that case, it's essentially telling you that you are indifferent between all of them. So same amount, yes, but at the end of the day, we have to compare you with someone else. And you cannot just say, because I hate it even more, so I shouldn't do it.
I have a question. So since you're going on down this road of human values, and I'm going to make some statements here about economics. So for me, North American economics is based oftentimes on, this atomistic view of individual humans maximizing their everything, right? Their preferences, or their outcomes, their livelihoods, their incomes. But when we look beyond American culture, values of, community are more embraced from, what people talk about since talking. So when we think about envy and wherein lies, and sometimes the answer is we can't model that, right? But and then for you as a scholar, how do you do it? But let me finish, which was, I might be happy for somebody else to have more than me, right? And so how does that, and I think it's important that we understand where we make lines of, well, we would love to include that, but we can't model that, at least yet. Maybe 20, 30 years we will. But do you have like a parking lot for all those kinds of values that don't fit the math at this point?
Yes. So I'm glad you asked this question. I have my PhD students, some are sitting there exactly working on this problem.
Yeah.
There has been some work mainly in behavioral economics.
Yeah.
That they're looking at what people actually value, even within the same culture.
Yeah.
And saying that, okay, what is it that you value, right? Do you value equal distribution?
Right.
One of the notions I kind of mentioned very briefly is this notion of equitability, or another notion which kind of comes out of it very similar to this. It's called inequality aversion. So it is this case that you actually have these distributive preferences in the sense that your preferences are not just over your own outcome, but you have preferences over the overall outcome. These are usually called as distributive preferences. And now you can have these notions of inequality aversion. So I prefer a scenario where you and I are getting almost equal solutions, right? So maybe perfectly equal or almost equal solutions. And then the question, which one of the questions I was raising there is that what are the hierarchy of these axioms, right? So maybe you care about this equality as long as the solutions are NV-free, or maybe other way around, right? You care about NV-freeness as long as they satisfy inequality aversion, right? In fact, there is actually has been shown that people care about inequality aversion as a more higher important thing than, let's say, NV-freeness.
Yeah.
But, and then this is actually, but also like something I want to mention is that those are in cases, most of the time in the cases that people are participating in some sort of bargaining games or negotiations where there's also this social factor comes into play, right? So it's a very interesting area of research. By the way, you asked about culture. There's also like a lot of discussions about, okay, these experiments have been done in this part of Europe, maybe West Germany versus East Germany. They have different culture. So Mark is working on exactly those type of topics.
And I hear you use equality, but of course now we've moved beyond equality to equity, but knowing, what the equitable solution is requires a lot of contextual information, which makes the math a lot harder.
Correct.
Because it blows up all the variables. It makes me honestly feel really good about human intelligence versus artificial intelligence. Because, when we talk about, well, we can't model that. Oh, we can't model that. I'm like, yes, we still have value because we all do this, right? We all do this.
That's right.
Okay, any more questions? All righty, so thank you so much, Dr. Hosseini, and thank you all. All righty. That's fun.
Thank you for inviting me.
No problem. They're gonna have you.